Let's look at the combustion just a little bit more. Obviously, we are mixing fuel and air or compressing a fuel mixture itself. There is combustion chemistry to produce thermal energy to expand air, for example, and pump into a piston or turbine generator to eventually generate electricity. It has limited efficiency because of losses and mechanical movements, friction, heat loss, etc. And it emits pollution. So pollutants now have become a bigger concern than the efficiency itself, even though along the way there have been many efforts to increase efficiency. So combustion efficiency is a percentage of total energy bound in the fuel that is transformed into useful power, in case you didn't already know, will be limited by the friction associated with all the mechanical steps in this figure that we saw. And the criteria pollutants will be formed because of the combustion chemistry and will be emitted in the exhaust. So the electric grid that relies on combustion is taking fuel and air and producing exhaust, and it's driving 80% of the world power production right now, with major pollutants like, of course, carbon dioxide, a greenhouse gas, water, which is not bad, but it's a feedback to the warming as well, nitrogen, and there are electrical. There are chemical reactions happening, producing hydrocarbon, carbon monoxide, noxious particulate matter, and so on, and creating serious problems of air quality, not only in urban areas but also drifting into many peri-urban and rural area. So 90% of the world's pollutants are produced by combustion. We don't always pay attention to this, but when you burn a tank of fossil fuel in a car, you use up to 400 pounds of oxygen. So you are reducing oxygen, even though the oxygen concentration in the atmosphere is almost 21%, so we don't have much to worry about yet. 94% of the world's CO2 is produced by combustion. So that combustion power generation, shown here with the gas turbine and other methods used, combined with hydroelectric, which is renewable to the extent of the hydrologic cycle, which is being affected by global warming as well, and nuclear, which is also renewable, with all its problems that we discussed in the other chapters. And they supply an electric grid, which is typically a central grid that's supplying industries, commercial buildings for universities, hotels, hospitals, and so on, as well as residences, all the way down to residences sometimes, living in remote places, right? How is the electric grid emerging or evolving over time? So you can see how this figure is going to be used to add more details along the way. Okay, there is our central generation. Now the grids are regularly accepting renewables from photovoltaic and wind energy, which adds the need for storage. So this is here the storage to deal with the intermittency because of the diurnal cycle, seasonal variability, and so on. And there is also combustion happening at the user's end, the consumer's end, because the industry may want to deal with the intermittency by having its own smaller gas turbine, as you remember the symbol, like a diesel generator, for example, which is highly polluting as well, especially in countries like India, where the power outage is unpredictable in terms of timing and unpredictable in terms of how long it would last, especially during the February, March, April months before the monsoon, because most of the country receives rain during June, July, August, September. Water resources begin to be exhausted because of agriculture and energy use in all sectors, and by March, April, May the country is parched thirsting for energy because it's hot. People are running ACs, refrigerators, fans, and so on, etc. So the complication on the grid demand, you can imagine, even if you add renewables. So commercial buildings run them as well, and in many Indian homes there are diesel generator units even at residential level. But the storage is shown here at every level. So this is one of the pathways where you have renewable contributing to the still ongoing central production with combustion and hydro and nuclear, but you are adding storage to deal with the ups and downs in the load flow or demands. Okay, so use of distributed generation like this one, the generation of power at the point of use, as we will see. This could take the form of fossil fuel power plants such as gas turbines, solar panels, fuel cells, or ground source heat pumps, which are basically geothermal energy sources that extract heat from under the ground. So Iceland and parts of Canada and other places in the world are using significant amounts of geothermal right now. The advantages of this distributed generation paradigm are threefold. Avoiding transmission losses, so up to 7% of the energy is often lost when you transmit electricity, especially long distances, those huge cables you see running across when you drive on highways outside of all inhabited regions and so on. Increasing reliability. So generating electricity at the point of use increases the reliability of electricity supply to the customer. Should the grid experience an outage, for example, distributed generation can power critical circuits at a minimum, like emergency hospitals, emergency lights, and so on, firehouses, etc. Capturing and using exhaust heat. This is kind of reducing loss of exhaust heat. With generation at the point of use, the heat in the exhaust can be captured and used to serve thermal loads like requirements for steam, hot water for bathing or running other instruments, chilled water for running meat factories, fish storage places, homes, etc., hospitals, thereby displace electricity and natural gas that would otherwise be required for other purposes. The fourth one is to improve energy storage. So fourth paradigm shift is the deployment of battery storage at both the central and distributed generation levels, as we will see. Okay. So the diurnal variations, intermittencies associated with wind and solar renewable sources is something that the grids have to worry about, and generation mechanisms, distributed versus central. Uncontrolled vehicle charging loads. So as the number of electric vehicles begin to increase, they'll be plugging in everywhere and demanding electricity. Now you go and pump in fossil fuel because they have a huge tank which is loaded up and stored. Even then, sometimes in remote places you might get petrol pumps or gasoline pumps that don't have availability, right? The demand for rapid ramping up of spinning reserves. There are places where the gas turbines keep spinning, not producing electricity, but when the demand goes up, they will have to start producing energy to meet the loads. Okay, so with a goal to provide resources that can absorb an increase in generation in the absence of load and discharge energy when the load exceeds the generating capacity. Okay, so you can see that the grid has to evolve along with the demand from electric vehicles. So you transform the system towards reducing emissions and greenhouse gases, but you increase the demand on grids at various places. So the grid itself has to evolve to meet these demands as well as the intermittencies from renewable energy generation. So distributed generation tends to deal with these.